Ever wondered how a robot could understand a task like put the milk in the fridge, and then visualize the entire process step by step? Today, we're diving into a revolutionary AI framework called Genie Envisioner, which is redefining how robots perceive, plan, and execute real-world tasks. This isn't just about following commands. It's about equipping machines with visual memory, predictive reasoning, and the ability to think through complex sequences, just like humans do. Let's start with the foundation. GEBase, the core video model driving this system. Traditional robotic AI often relies on short-term visual memory, processing only the most recent video frames to make decisions. But GEBase introduces long-term sparse memory, a breakthrough that lets robots retain critical visual information over extended sequences. Think of it as a robot's brain storing key snapshots of its environment, not every single frame. This allows it to detect patterns over time, like recognizing a cup drifting toward the edge of a table even if it's not currently in view. Now here's where the system gets truly sophisticated. GEBase doesn't just use one camera, it leverages three: a head-mounted camera and two wrist-mounted ones, mimicking a robot's eyes on each arm. This multi-view setup enables the robot to perceive its environment from multiple angles, much like how humans use binocular vision to judge depth. But how does it make sense of all this visual data? The answer lies in a shared latent space, an abstract mathematical representation that captures the essential features of all camera feeds. Imagine compressing a 3D scene into a simplified code that preserves critical details. To refine this, the system adds noise maps, which act like a painter's sketch, guiding the AI to generate the next video chunk with precision. Meanwhile, positional embeddings ensure temporal and spatial alignment, telling the model where each frame fits in the timeline and which camera it originated from. But here's where it gets really smart: a hybrid attention mechanism. Picture it as a team of specialists. Some parts of the AI focus on individual camera views, analyzing details like motion or object orientation. Others cross-reference all views to spot connections, like noticing a hand reaching for a cup while the head camera tracks its trajectory. This balance lets the robot handle complex tasks efficiently without getting overwhelmed by data. Now, how does GEBase learn to do all this? Researchers trained it on a massive dataset of real-world robotic actions, millions of videos showing robots performing tasks like washing dishes, organizing shelves, or assembling parts. The training used a two-stage process. First, teaching the model to handle fast-paced, dynamic movements, then refining it to match the slower, precise control required for physical execution. But video generation alone isn't enough. Enter GEAct, the system's action engine. While GEBase predicts what might happen, GEAct translates those predictions into real-world actions. It decodes instructions like fold the shirt into precise motor commands, adapting to new tools or unexpected obstacles. This module uses a lightweight architecture to ensure low latency, high-precision control, even in dynamic environments. And there's more: GESIM, a virtual simulator that lets robots practice safely. Imagine training a robot to assemble a car in a digital twin of the real world, testing thousands of scenarios, including failures, without physical risk. GESIM uses generative models to create realistic, what-if scenarios, teaching robots resilience and adaptability. This accelerates development and ensures smoother real-world performance. Finally, we need a way to measure progress. That's where EWMBench comes in. Traditional metrics like image quality fall short when evaluating robotic task success. EWMBench assesses how well a model predicts real-world outcomes. Does the robot's video prediction align with actual physics? Can it plan steps to achieve a goal? This benchmark ensures the system isn't just generating pretty visuals, but functional intelligence. Genie Envisioner isn't just a technical achievement, it's a glimpse into the future of robotics. By merging video understanding, predictive planning, and real-time action, this framework bridges the gap between digital AI and physical reality. As research advances, we're not just building smarter robots, we're creating collaborators that can navigate our world with intuition, adaptability, and a touch of human-like reasoning. So the next time you see a robot folding a shirt or organizing a shelf, remember, it's not just following code. It's thinking, learning, and visualizing the future, one frame at a time.